Welcome to lesson 9 of stochastic processes. Everything in the past lessons assumed the chain moves in discrete steps. Step 1, step 2, step 3, and we use the n to represent the number of steps. Time was just a counter, and we never asked how long anything actually took, other than in terms of steps. Now we let the chain live in continuous time. It sits in a state for a while, then jumps. That raises the question that simply did not exist before. How long does it wait? How long are we in a state when we use continuous time? The answer is interesting in the sense that we don't really get to choose. The Markov property carried over to continuous time forces the holding times to be exponentially distributed. Nothing else is possible. That is the main theorem of this lesson, and we're going to prove that. It'll take a few slides to do that. Towards the end of the lesson, we will encounter the counting processes and the two conditions that make them tractable, and that'll set us up for the Poisson process in lesson 10. As I mentioned, so far, time was measured in steps, and the real duration was ignored. Now the state space stays discrete, so it's either a finite set of states or countably infinite, but transitions happen at any moment. The Markov chain holds or stays in a state for a random length of time and then jumps. And we'll let x, capital X, greater than 0 be the holding time. And we also define a Markov property in a continuous version. It has no memory, and it's saying the probability of having already weighted b, this here, the chance of weighting a further a, in other words, a plus b, is the same as it was at the start. So this here. Okay, so take a look at this because we're going to use this to prove the statement about the holding times. Okay, let's proceed to the next slide. The holding time in a given state for a continuous time Markov chain was a discrete state space. It must be exponential. We're going to prove that in the next few slides. I have it stated more formally here in the theorem. If a random variable x with range 0 to infinity satisfies the continuous memoryless property, then x is exponentially distributed. So we'll start the proof here and it'll continue on the next slide. So we have our memoryless property here, and we also have the conditional probability definition. Probability of A given B is the probability of A and B divided by the probability of B. So we want to apply that here. So we have, this is our B in this equation, and this is our A, but this equals probability X is greater than A. Then we just need to do this part here. So the probability of A and B, well, these two intersect, right? So the probability of these two together, which I've written out here, is just the probability X is greater than A and B. And then this is our B. So we just bring that down. So now we have the probability that X is greater than A is the probability of X is greater than A plus B divided by the probability X is greater than B. And we can write this way here. And then just in terms of simplification of the notation, we'll write G of A equals the probability that X is greater than A. And then we can rewrite this equation here. It's just G of A plus B equals G of A times G of B. And just a note, if you recall from lesson 6 and 6a, we use G to be a generating function. That has nothing to do with the usage of G here. I just happen to use the same letter, so just to avoid any confusion. Okay, so let's take this and let's see what we can do with this in terms of proving an exponential distribution. let's continue with the proof. We're going to take x to be rational first. And I'll come back to this first line in a minute because we'll need that on the next slide. But let's first assume that x is rational. So it's of the form m over n, where m and n are positive integers. Then we can write g of m divided by n is just g of 1 over n m times. And then using our property of g, in other words, g of a times b is g of a times g of b. We just use that m, apply that m times, and we get g of 1 over n to the m power. So this equals this. Then we raise both sides to the n power. So we have this equals this. Then we just bring the n inside. Then just working in reverse from what we had up here, we have this equals this. But in this case, now there's n of these. Here was m, now there's n of these. So this is just g of 1 to the m power. So we have g of m divided by n to the n power equals g of 1 to the m power. Raising the above, both sides of this, to the 1 over n power gives us the g of m over n equals g of 1 to the m over n power. Okay, so this works for any rational number. We'd like to show it, we like to show this where x is real, but so far we've only shown it for the rational numbers. So we'll do that on the next slide, but I want to come back to this first point here because we need this on the first slide, on the next slide. The g of x is monotonically decreasing in x. Remember, g of x is the probability of remaining in the state for x units of time. So as you increase that, as you increase x, the probability of remaining in the state becomes less and less, right? It's just a longer amount of time. So this function is monotonically decreasing. All right, so keep that in mind when we get to the next slide. Okay, so we're almost done. We want to extend our proof to the case where x is a real number. So take any real number x and we squeeze it between two sequences of rationals. Just as a reminder, we can get arbitrarily close to any real number with a rational number, either below or above. And so we'll create a sequence, two sequences, one approaching x from below and one approaching x from above. And the trick here is that we know our identity holds for the sequence Qn and R sub n. And we have the monotonicity of G, which I just mentioned, that preserves the inequality. So we have G of 1 to the Q of n, Q sub n power equals G of Q sub n. And this is greater than G of x because of the monotonicity. And then G of x is greater than G of R sub n, which equals G of 1 to the R sub n power. So as n approaches infinity, in other words, as these sequences get closer and closer to x, both outer terms tend to g to the 1 to the x power, trapping the middle. So in the limit, this g of x equals g of 1 to the x power. That's what we wanted to prove. And then we can write this as an exponential function. We just let lambda equal minus log g of 1. So if you plug that in here, the minuses cancel. Then the exponential of the log is just the term in here, g of 1 to the x power. And that's what we have here. Okay, so we've proven that the holding function, the density function for the holding time is exponential, and then this is the cumulative distribution. So of course it eventually accumulates to 1, and so you subtract what's being accumulated here, and that's it. So that's our proof, and it's pretty amazing. So we just assume the memoryless property, and we were forced to conclude that the holding time is exponentially distributed. The theorem we just proved holds in the opposite direction. We can show that here. If x is an exponential distribution with rate lambda, we can show that the memoryless property follows. So we start here, probability that x is greater than a plus b, given that x is greater than b, and then using the definition of continuous probability, we have this here. Then, as we mentioned before, these two events overlap, so this is the same as the probability that x is greater than a plus b. Then we take our assumption of exponential distribution, and so this is e to the minus lambda a plus b, and this is e to the minus lambda b, and then the lambda b's, the minus lambda b's cancel, and you get e to the minus lambda a, which is, again, from our assumption here, that's the probability x is greater than a. And so we have this equals this, and if you recall from the second slide in this lesson, that was the Markov, a continuous Markov property without memory. And so the exponential distribution is the only continuous distribution on 0 to infinity with the memoryless property. A continuous time Markov chain is therefore a set of states, transition probabilities between them, and exponential holding times. The holding times are independent of one another. We get that from these property here. I have an example here of a continuous time Markov chain. So we have 3 states, and on the left we have the probabilities of going between the states. So you can go from 0 to 1 was probability 1/2, and to state 2 was probability 1/2, and so on. So that's part of the definition. Then you also need holding times, and this is our lambda in the exponential function. So state 0 has rate 6, state 1 has rate 18, and state 2 has rate 12. A higher rate means a shorter expected stay, so it's sort of the rate at which you're leaving. So if you're leaving at a faster rate, you would be there at less time. So state 1 is the most fleeting, since that has the highest rate. And the other thing to mention is that these zeros here are not a coincidence. Any continuous time Markov chain cannot jump from a state back to itself. So these are always 0. You'll see that. You still have a holding time, but it's the probability is that you leave and you go somewhere else. Something called a counting process is the next topic we want to talk about. A process, a random process, n of t, t greater than or equal to 0, is a counting process of n of t is the number of events by time. Events are often called arrivals in this case. So we start out with it being 0, and then it increases. So n of t is greater than or equal to n of s for t greater than s. It's so just in words, it starts at 0 and never decreases. Events accumulate. And some examples: cans sold by a vending machine, cars crossing an intersection would both be counting processes. A counting process is not automatically a Markov process. We need 2 additional conditions in order to make a counting process Markov, and we'll see that as we continue. The first of the 2 conditions to make a counting process a Markov process is independent increments, which I discuss here. So the number of events in disjoint time intervals are independent formally for any times t0, t1, tm. The following are independent. So the number of events between t0 and t1 is independent of the number of events between t1 and t2, and so on. So for our two examples, for the vending machine, this may be true. It's plausible. The vending machine, what was bought in the morning, for example, may not say much about what's going to be purchased in the afternoon. In terms of the intersection, if you're busy here in, say, the first time interval, then it's likely that might take some time to dissipate. So you may be this interval may affect the counts here and so on. So it's doubtful that an intersection, at least the busy intersection, meets this requirement. It may be, if you have a very lightly traveled intersection, things may just pretty much be the same all day long. But so, think of something in a city where you have rush hour, and if it turns out to be a really bad rush hour, you may have a couple hours after that where the count is still higher because of what happened earlier. So that would violate this. Okay, so that's just relative to these examples here. You need more precise information to be, exact on this. The second condition is stationary increments. The distribution of the number of events depends only on the length of the interval and not on when it starts. So that's stationary increments. Then I have an example here and a counterexample. A 24-hour mini market with a constant arrival rate plausibly qualifies. So you have the same distribution of events regardless of time of day. It just depends on the length of the interval. So that may be the case here. And then a machine, for example, a printer in an office building would not, because for example, the mornings or even during the day, you have one distribution for the number of people using the printer. And then at night, you would have a different distribution. You maybe only have a few people or nobody at all using the printer at night. So the two conditions don't imply each other. And I have an example of each where you have one condition and not the other. So you could have independent but not stationary. And the example I give here is a coffee shop. It's busy at breakfast, maybe quiet in the middle of the afternoon at 3. But customers come on their own errands. So 1 hour tells you nothing about the next. So this would be independent, but not stationary. Then stationary, but dependent. Let the counting process be t times the normal distribution, the bell-shaped curve. So every increment of length t has the same distribution, t times z. The dependence is the shared z. Two windows of the same length are not merely alike. They are the same random variable, so knowing one fixes the other exactly. So we have stationary, but there's this dependence based on the distribution z. I have a little bit more of an explanation of this on the next slide. Concerning the second example on the last slide, where we had this normal distribution, I just wanted to go into a little bit more detail. So we had n of t equals t times z, where z was a normal distribution. So the increment over any interval of length t is given by this here. We have n of s plus t minus n of s. And then just using this here, we have s plus t times z minus s times z, and we get t times z. So the same distribution regardless of where the interval starts. So the increments are stationary. But now we compare the join, this here, the union, and the product, and they should be the same if they're independent, but they're not. So if we just take an example here, you have the number of arrivals between 1 and 0, if that's greater than 0, and the number of arrivals between 2 and 3, time 2 and 3, is less than 0, then this here, just using this equation up here, this is z, and then n of z is 0. So this is the same as z greater than 0. And again, using this up here, this is the same as 3z minus 2z, which is 1z less than 0. And so the probability that z is less than 0 and greater than 0 is 0. But if you write this as a product, which would be true if these were independent events, you would have this, which is the probability that z is greater than 0. It's a normal distribution, so the probability is 1/2. And then this is the probability z is less than 0. And again, that's 1/2 because you have a normal distribution. So this is 1/4. These two are not equal, so these two events here are not independent. Okay, so that verifies our counterexample in the second case. You need both conditions in order to have this additional capability. So that's it for this lesson. I have a summary on the next slide, and then a little bit of an advanced description of the following lesson. So a summary or some takeaways from lesson 9. Continuous time focuses us to model how long the chain waits or holds in a given state. Memoryless implies exponential holding times. We proved that, and nothing else. That's the only. So we proved it in 2 directions. Counting processes start at 0 and never decrease. This was the monotonic decreasing property. And independent and stationary increments are separate conditions. And we just gave examples where you could have one and not the other. Then we have something called a Lévy process. A process with both independent and stationary increments is also called a Lévy process after Paul Lévy. So in other words, that's what we just defined. The 2 best known examples are the Wiener process, better known as Brownian motion, and the Poisson process, which we're going to talk about in the next lesson. So the Poisson process, a counting process with both conditions plus a rate. Remember, we talked about the rate for the holding times. So we'll get into this in a lot more detail in the next lesson. Its axioms, it's referring to the Poisson process, and the theorems that follow from them, why the interarrival times turn out to also be exponential, and then we'll talk about the compound Poisson process also in the next lesson.